variables is very, very helpful for us. We look at all kinds of stuff like this. A lot of times it might be like we could look at gas prices, right? So over time we could look at what's happening to gas prices. Right now, they're going up. Gas prices are much more volatile though. Hopefully one day they might go back down a little bit. They go up and down a lot, right? We might look at something like the number of coronavirus cases over time, right? If you're just looking at number of coronavirus cases, it always goes up. It never goes down. Because if today we had no more coronavirus, period, if it just ceased to exist, at the very best, it would be just a flat line, right? It's not going to go back down because people have had it, already had it, and you can't reverse that. You could look at the cases per day, and then you're going to see it go up and down from time to time. So all kinds of things that you can look at. This is just one example. We'll use some that are like a little bit more simple and don't have as many data points here so that we can make predictions with this. But in the real world, you would be looking at lots. The more data you have, the better your predictions will be. So, so we have this. What I want to know is this looks more or less like a line, right? It's not a perfect line, but it's close. So, is there a perfect line that will hit every one of those points? There's not one that will hit every point. But we could put one through here that's more or less pretty close, right? So, I'm just going to start with y equals x right here. What do you guys think about my y-intercept? What should my y-intercept be? It's got to be negative something. You guys want to try negative 5? Okay, that gets a lot of them. Let's try. I think 6 is too low. 5.5. That kind of splits between them, doesn't it? Now, it actually kind of worked here for our slope to be 1, which makes sense because for every one grade, every 1 year, you go up 1 grade, right? So that you would expect the slope to be 1. If we had several people who had failed grades here, it might change whether or not that worked, right? But more or less, like for example, if you are 11 years old, or let's go right here, because if you're 12 years old, you are either in the 6th grade or the 7th grade, unless you have failed a grade or been held back or something. So, so this looks like a pretty good line, right? Y equals x minus 5.5. In fact, I feel like this is probably going to be a good line for what we have. So let's use that as our line of best fit, okay? So, we're going to sketch, actually, you don't have to draw your graph here. I'm gonna export this so I can put it there. And because there's so many dots, you don't have to. I'll put this here. All right, and then, so we said the equation of that line that we came up with was y equals x minus 5.5. And what does our x stand for? What do we put in that x column? What in our x column, what does it stand for? So what does it represent? It shouldn't be a number. Nope, not slope. It is our age, right? Because in the x column of that table, we were entering the age of all of the students, right? What's the y stand for? It is grade. Okay, so the age, it is their age in years. So if you said years instead for x, that would be okay. Grade is y. Okay, so using your line to predict, what grade is a 7-year-old supposed to be in? Okay, so we're going to use our line to predict. So what should I do with that 7? Where should I plug that in? for the x, right? Because x is 7 is an age, so it goes there. So I'm going to have y equals 7 minus 5.5. And if we do 7 minus 5.5, we are going to get 1.5, right? 2.5. No, 1.5. There. Now, are you ever in the 1.5 grade? No, but what does this tell us? I would say first or second grade, right? Because we know that although you would round up, if you have a 7-year-old, they could be in either first or second grade. If they have a really early birthday, they might turn 7 while they're still in the first grade. Or if they have a really late birthday, they could possibly be in the second grade. Especially when you're talking about like middle of the year, right? So I would say first or second here. Okay, another thing that you can do with this data here is you can say if a student is a junior in college, and we're going to call that the 15th grade, right? So you got 12th grade, and then you'll have 13th, 14th, 15th would be your junior year in college. So we're going to sort of look outside of our data. So I only had you guys put people on this list that were between kindergarten and 12th grade. I told you to stop at 12th grade. Some of you might have had some brothers or sisters that are in college, but you didn't include them on this list. So, if I want to know how old you should be in the 15th grade, where's my, there we go, sorry. Let's go back. Oh, I don't want to do that. So, in the 15th grade, if I want to use this equation, where would I plug 15 in? Okay, at that, not at the 5.5, that's not a variable. It's y equals x minus 5.5. The grade is our y, that's our grade. So this is a lot like what we were doing when we were doing stuff with our x and y intercepts, when we were doing those word problems. So the 15 is going to go here. And we will need to solve for that x. So we'd have to add 5.5. And so if we do that, we get 20.5 for our age. So 20.5 years old. And I guess you can be 20 and a half, so we'll leave it like that. But somewhere between 20 and 21 when you're a junior in college. And does anybody have a brother or sister that's junior in college? Is that about right? About right. Is Kason junior? No, Micah. Micah's, yeah. So, about to turn 21, yeah. This is reasonable. So our line makes a pretty good prediction here. Now what we did with that information is we extrapolated the data. Okay, that's a fancy word, extrapolate. Okay, so sometimes extrapolating is very accurate. So extrapolating is like all of our data here was just from 0 or kindergarten to 12th grade, right? But we said, hey, we're going to take this trend and we're going to apply it beyond where we're at, right? So we're going to apply it to college grades. And so in this case, it worked pretty well. Pretty well, right? We got what was about normal. But those of you that have brothers and sisters that are in college, they probably went straight to college, right? And they did not skip any years and they didn't go back to college. And so they just followed this trend. But if we looked at all the college data, how many of you have somebody in your family who did not go to college right out of high school, but later went back to college? Probably lots of you, right? Yeah, so like, if we included those people, right, there might be somebody who is 35 who is a junior in college, or 42 or something, right? Somebody's going back to school. So if you looked at all the people in college, it might not necessarily be accurate. I know when I was in college, there was always several people that were in my classes from time to time that were older, that were going back to school. So it might not be quite as accurate. So this would probably be true if you go straight out of school, but if you do not, then our line probably would not hold up, right? Okay, questions. Now, what we were looking at here is a pretty fixed situation, right? Your age and your grade should go together pretty well. But they don't always. So, the next thing that we're going to look at is some data that is already provided. So this came from a textbook. I believe it should be pretty accurate. And let me change this so it shows up a little bit bigger here. So what we're looking at here, it says below you will find the percentage of doctors who are male for given years. X equals year, Y equals percentage of doctors who are male. Okay? So what we have here is in 1960, 98% of doctors were male. In 1970, only 93% were male. In 2000, it was down to 76%. In 2010, it was 71%. This came from an older textbook. It stopped there. We could give it a quick Google just to see, but I'm not going to add the data because I don't know how accurate it is. So, what percentage of doctors are male? This is 64%, but I'm not sure where that data is coming from. That's a quick Google, so we're not going to go with that. But it would kind of match what we're seeing here, right? If we added it, let's add it and just see what it looks like. So, if I add in 2020, if I add 64, does that look like it's pretty accurate? It looks like it's falling. Let's just leave it because that looks like a trend that seems to fit what's happening here. So, so this is what we're seeing. We're still seeing more male doctors than female, but not overwhelming like it was in 1960, right? 1960, if you were a female doctor, then that was very rare. Now, probably most of you have seen a doctor at some point that is female, right? Or know someone who is a doctor that is female. So what I want us to do here is I want us to try to get a line to fit. So we're going to take these points and we're just going to move them till we get a line that fits pretty good. So you can see, like this line right here, it's not hitting every point exactly. I mean, it is touching every point, but it's not hitting every single point right in the center, right? They're a little bit off, but would you say we're pretty good right here? Does that look pretty, like a pretty good line, you think? Good enough for what we're doing right now, sort of an introduction. So it tells me down here what those points are. So I'm going to jot them down. Let's see here. Okay, so the 2 points that I have picked here are, it tells me 1961.7, sorry, 0.7, and 97.5. That's my first point that it gives me. And then my other point is 2000 17.6, and then 65.5. So let's drop those down. Now, we need to write the equation of that line because it's much easier to use a line to predict things if we have an equation for that line. So, if I want to write the equation of a line, Passion, what have I got to find first? What do I need to find first when we're finding the equation? Slope, right? And how do I find the slope for this one? All right, so these are our points right here. We got 1961.7 is our x-coordinate, and then 97.5 is our y. And then we got 2017.6, and then 65.5 is our y. So even though these numbers are kind of ugly, we just have to do slope formula with them. What would that look like, Ayla? Good. And so whenever we subtract those, we're going to get 32, I think, on the top. And then I should let you guys. And this will be something you're allowed to use a calculator, negative 55.9, so divide that by 55.9, and we get negative 0.57. I'm going to round this off to 3 decimal places, 572. It keeps on going, but we're going to round there. All right, this, although it's not a fraction like we're used to seeing, this is our slope. Okay, now what do I have to do? Now I've got to find the y-intercept, right? So we're going to do that. Even though these numbers are weird, we're going to do it the same way we've been doing it, right? So which point do you want to use, Jada, the top or bottom one? Okay, so if we use that top point, we would have 97.5 as our y-coordinate. It is going to equal the slope, negative 0.572, times our x-coordinate, 1961.7, plus b. And so we'll use our calculator to multiply those together. I know I didn't have you go get yours, but I'll just do it up here. So we're going to get 97.5 equals negative 1122.09 plus b. And then what would we do? Yeah. And so that y-intercept is going to be 1219.59. So we end up with our equation being y equals negative 0.572, that's our slope, x plus 1219.59. Yes. Yeah, it's the exact same thing we've been doing, right? Exact same thing we've been doing, right? So you did the exact same thing on the test where you had 2 points, right? So if I gave you one that said 2, 5 and 3, 7, right? You'd find the slope, you'd find the y-intercept, you'd write the equation. It's the exact same thing we've been doing, It's just going to have bigger numbers, right? And this is calculator active. I won't give these to you without a calculator. I realize I didn't have you come get them right now, so take my word for it on the calculator part, but we'll use those here in a minute. So, yes, you may be asked to do this. Okay? So it's the same thing. The numbers are just a little uglier, but that's what the calculator's for, to help us deal with those uglier numbers. Okay? All right, so questions. All right, in this equation, Julian, get your head up. What does my x stand for? What does it represent? It is not the number of doctors. Not the x. Let's go back to our... Yep, the x. X is the year, right? In the x column, we put the years. And in the y column, what is it? Almost, what'd you say? Percentage of male doctors. Or let's say doctors that are male. Okay. So, percentage of doctors that are male. So, this would be, it's not the number of male doctors, because there's more than 98 male doctors in 1960, right? It's the percentage of doctors who are male. All right, so, what percentage of doctors do you predict will be male in 2025? So what we're doing here is we're taking the data we've got and we're extrapolating that data, right? We're saying, if this trend continues, how many doctors are going to be male in 2025? So what would we do with our line here to make that prediction? Wade? Yes. Okay. So if we do that, and this is calculator active, just typing it in here, I get 61.29%. So 61% in 2025, which is coming up pretty soon, all right? Okay. Okay. All right. This says, what percentage of doctors do you predict will be male in 2080? What are we going to do for that part? Right. Exactly. Same thing we just did. Okay. So when I do that, I get 29.83%. Okay, so let's talk about the validity of this, okay? Because this is, whenever you are, this type of math is really useful in a lot of different areas. So this is something you might be doing if you are researching, any kind of trend like this that you see. So, does it seem plausible that in 2025, 61.29% of doctors would be male? That seem plausible? Could happen? I mean, because when we just looked it up a little bit ago, in 2020 it was 64. So going down to about 61 seems reasonable, right? Seems like that would happen. In 2080, does it seem likely that only 29.8, about 30% of doctors are going to be male?
It don't really sound
Okay? So eventually, do you think this trend would quit applying? I think in the short term, we might see this happening, but let me zoom out right here. Right here in the year 2132, which none of us are probably going to be around to see. But when we get there, what percentage of doctors are male? 0. Then after that, like in 2150, what percentage of doctors are male? Like -10. So we know at some point this has got to quit because we can't have negative percentages, right? The lowest we could possibly have is 0%, right? So it is possible to have 0% of doctors are male. Okay? Julian and Passion, get your heads up. I want to see your faces. Okay? All right. So it is possible to have 0. Both of you, put your heads up. Heads up. Sit up. Sit up. Okay? All right. So it is possible to have 0% male doctors. Is it likely that we will ever see no male doctors in the whole world? Probably very unlikely that that will actually happen. In my estimate of things, I think it's unlikely that we'll see 29% of doctors being male. Right? What seems more plausible? What seems was eventually going to happen? More 50-50, right? I think there's a chance it might even stay a little higher percentage male, just because, women are probably a little more likely to not work than men, although trends change all the time, and that might be the case. But certainly being a, brain surgeon and raising young children might not always be compatible with each other. That might be difficult to do. Not that it can't be done. It's just there might not be as many that are doing that, but it could happen, right? So I think we're more likely to see it even out, right? Although right now in medical schools, more students are female than male. And in college in general, I read the other day that 60% of students in college are female. So way more females are going to college than males. That's not medical school, that's just in general. But I think in medical schools, there are more females in medical school right now than there are male. So I think it's possible we may see this 61 drop off even a little quicker, but then I don't think we're going to see it 30%, right? You never know. Human behavior can be strange, but yeah. So, and we could look at this in a lot of different fields, right? Because you certainly would see this happening in a lot of different fields. If you go back to the 60s, most fields were male-dominated except for a few, right? Because there were a lot of women who did not work. Most of the workers were male. That's much less common today than it was then. So it's kind of interesting to look at these sort of trends, see what's happening. You can make predictions based on it, but you have to be careful with your predictions. Because if you make these predictions based off of what's happening right now, it probably does not apply in 2080. That's called extrapolating the data there. You're going way outside of your data, and this trend may not continue that long, right? So, for example, if we did the same thing with, the gas prices right now. If we looked at gas prices just over the last few months and drew a line for that, then gas would cost $20 a gallon in no time, right? But hopefully, that will not be the case, right? It's going to even back out. So linear trends for a lot of things do not continue forever, and you do not want to look at them like they continue forever. Questions? All right, so I need to make sure everybody has their computer, and we're going to look at the second set of notes. So that was by hand. Oh, I've got it. All right, that was looking at how to do this by hand. So whenever I did that, I was just kind of guessing, right? I just moved those points on the graph as close as I could But as you can imagine, if I were to write an article about this and talk about the number of doctors and trends that are happening, then would it sound good if I said I just came up with a line based on my best guess? That would not be very valid, right? So we are going to learn a better way. And this should say 5.15, but I just changed it. There's 2 pages. Yes. Here. So we're going to need to use a Desmos calculator. If you have not used Desmos before, just go to www.desmos.com. It's a Google affiliated. Yes, the one that says graphing calculator. I believe you guys use this in 8th grade, so right? It does not matter if you save it or not, so you don't necessarily have to log in. But if you are ever doing like something where you know you're going to need it later, you might log in. So, we used to do all of this on the graphing calculator, but the state, the online embedded calculator that they put on your exam is Desmos. It's the same program. So you have access to Desmos whenever you take that exam, and I can actually put Desmos in my test as well. So we're going to look at starting these. We won't get all the way through. Say what happens in the screen. Why'd it go black? There we go. Okay. So, I have been calling those lines that we just made our predicting lines a line of best fit. There are some other phrases that you'll see sometimes. Most common are going to be either linear regression, linear model, or a trend line, okay, along with line of best fit. So if you see any of those phrases, sometimes instead of calling it linear model, they might just say the model, but right now we'll only be looking at linear models. Both sheets for you. So, if we're asked for any of those, it's asking us to do the same thing, right? There's not a difference between these. So, what I want you to do here first is we're going to do one more by hand. So, I want you guys to graph these points for me on that coordinate plane. So, graph those points for me. Alright, so hopefully you're able to graph those. Your points should look like this here. Alright, and we want to draw a line of best fit. So I want you to just draw in a straight line there that fits your data well. Are you going to be able to hit every point?
Well, yeah, I mean, if you draw the
Not.
line,
Okay, is it hitting directly on every point? Right, so this is not a perfect line. Now, probably most of your lines look similar to what I have here. I've got basically these 3 points are just a little above the line, and these 2 points are a little below the line. So I could go through like I did on the last problem. I could come up with the points here. We could write that equation by hand. Or, if we did that, if I had every single one of you do that, you'd probably end up with different lines, right? Because your estimate might be a little bit different than somebody else's estimate. Or, the calculator has a function that uses what's called a least squares regression. And it will calculate the statistically best line of best fit. So meaning statistically speaking, this line is the closest to all the points. It factors in all the points. So we're going to do this on the calculator. So I need everybody typing this in on the computer as we go. So you're on Desmos. Just go back here where the graphing calculator, it should be blank. It should look like this here. Okay. All right, so the first thing that you're going to do is you've got to enter your data. It's really simple in Desmos. You're just going to hit this plus right here, and you're going to tell it table. And it'll just show up with an X1 and Y1 in that column. And you're going to type in those numbers. So there's a plus sign up here in the corner. When you click it, you're going to tell it table. Okay, so everybody make sure you're doing this. I'm going to come around and check, see what we got here. Yep, and then just enter these data points. And the nice thing is it graphs it for you there as you go. You can see it might look a little bit different because we're zoomed in a little bit differently. But it's the same point. Make sure everybody has those points there. So hit the plus right there. We are on Desmos right now. We're working on this set. Yes, if you practice that over here, I'm going to be able to see that. Alright, so I think everybody has this line. So the calculator, we could do this on the graphing calculator as well. I'm going to teach you on Desmos instead, and the main reason is that you should be able to use Desmos at home. As long as you have the internet, you can get to Desmos, you can use it, whereas I don't send the graphing calculators home. Plus, Desmos is easier to use, in my opinion. All right, so in this first column, notice it's called X1, and the second column is called Y1. Okay? So what we're going to type in is we're going to type in Y1. You're just typing Y and a 1. It'll automatically make that 1 be a subscript, a little 1 down there at the bottom. And then you're going to do the squiggle sign. Okay? That is shift, and it's the key above your tab. Shift, the key above your tab is going to give you that squiggle sign. Just type Y and then 1. Yep. And it should go down to the bottom. So Y1 squiggle. And then X1 plus B. Okay? So, and again, type that X1, you just type X and a 1 behind it, and it'll be there. So, you're typing, I'm going to write it bigger over here too in case you can't see it. So, you're typing in Y1 squiggle X1 plus B. And as you do that, you should see a line show up. Everybody got a line? Check and make sure everybody's got a line. Okay. All right, everybody has a line. That's great. Okay, now you should see over here you have, okay, over here you have several numbers, okay, and so you've got an M right here of 2.5. So that means your equation is y equals, the M is 2.5 and the B is 4.8. So 2.5x plus 4.8. It's giving you the equation of the line, right? So, write it on your paper, yeah. Yeah, if you type it in on another line, it's just going to graph another line right on that same place. So, because this is what it's graphing. So, we're going to write this down. This is our line of best fit. Okay? Slope is 2.5. Y-intercept is 4.8. Statistically speaking, this is the best possible graph. It's the closest to the most points, right? Then you also see these two values here. You have an R squared and an R, okay? The R there, wait, I think I might show you this on the other one. Yeah, okay, go to the next slide. R is called the correlation coefficient. So there is a number R called the correlation coefficient that describes how closely the line fits the data, because I think we can all agree here that we're not hitting all of those points perfectly. In fact, if you zoom in enough, you can see that the points don't hit the line perfectly. They're close, but they don't hit the line perfectly. If the correlation coefficient is positive, then the graph is increasing. From left to right. And you can see on this one, we did have a positive correlation coefficient, and we had a positive slope on that line, right? If the correlation coefficient is that should say negative. Let's change that. Fix those. Is negative, then the graph is decreasing from left to right. All right, so if we see a positive correlation, that means that our data points seem to be increasing. If we see a negative correlation, that tells us that this is decreasing. But that's not the only thing we want to know from that correlation coefficient. Another thing we want to know is this line a good fit or not, right? Is it close to the points or is it pretty far off? So if the correlation coefficient is close to 1 or negative 1, then the line fits the data well. Okay. If it's far away, it's poor. So our correlation coefficient was 0.9976. So our correlation coefficient is 0.9976. Okay. Is that close to 1? I realize close is a very relative term, but pretty close to 1, right? So our data is pretty good, right? So although this is not perfect, it's going to give you something pretty close. Now, if our correlation coefficient was 0.2, that would be terrible, and you should not use that to make predictions because your data does not predict that well, right? So you don't want to use, whenever you do this, if you find that you don't really have a very strong correlation, you don't want to make very strong claims about what's happening there, right? So, let's see if we can do this one right here. And let me see, how can I do, this already has the data in it, let's see. Alright, I need to, I want to copy, alright. Not really what I want. I think I need, hold on. Let's see, let me do this instead. Okay. Alright, I'm going to send you this email. So go to your email real quick and click on that link in the email, which is hopefully going to bring up this here. Is it working? Okay. All right, so everybody go there. I also, because we're running short on time, I want you to click log in. Tell it log in with Google. So you get logged in. Does it already say your name right here? You don't have the email? Refresh it, because. Okay, log in. Alright. Log in so that it says your name here, so that you're logged in. And then go over here and click save. That way, if we don't get finished with answering this question, we will be able to look back at it tomorrow. Okay, so it'll save where you're at. So, log in, click save. Has everybody done that? We have got 7 minutes left. I think you can hold it.
Is it really worth it?
All right. Okay. Is everybody? Now, before we get started with this, I don't see any dots here. I see no dots. But I've got the data in the table. So, why is nothing showing up? All right, so look at my X's, right? And my Y's. Now, I could just zoom out, but the problem with zooming out is if you zoom out, the points, like this is not a very good picture, right? So, what we're going to do, hit the little wrench up in the corner. Now let's look at our x's. What is our lowest x that we see here?
410. No, 190.
195. So right here, if you hit the wrench where it says x-axis, I'm going to make that lowest one 195. And then, what's our highest x value we have? 7790. So 7790. Okay, that's just a good starting place. I could have put 0 to 8,000 or something like that. This is a good starting place, right? So I put my very lowest here and my very highest here for the x's. Then I want to go to the y's. What's my very lowest y value that I see for either one of these columns? 55. What's the highest that we see? I think so, 950. And then so that gives me a pretty good picture, but see how I've got like these points that are way over here on the edge? I might want to zoom out a little bit more so that I can see everything.